Good afternoon, everybody. Today I'm going to talk about a 2009 study done by Google. And it was concerning memory failures in their fleet of servers. And in response to some of the questions that we've gotten from our customers, we designed a product. And when I saw this paper from Google, I came up with my own paper, which is hypothesizing that could those memory failures be caused by design flaws. So first of all, let's take a look at what was the Google study. Well, it was a pretty famous paper, at least in our circles, when it comes to memory analysis. It was called DRAM Errors in the Wild, a Large-Scale Field Study. And basically what Google tried to do was they tried to make sense of all the failures that they found in their fleet of servers. And what they concluded was that the failures were orders of magnitude more prevalent than advertised, which means when they looked at the specs of the DRAM parts and the DIMMs, they would get a particular advertised rate of failure. And what they found was that their failure rate was much greater. There was no specific conclusion that could be reached as to the source of these errors. And they noted that some of the failures followed the server versus the memory. Versus they would change out the memory, the server would fail again with a different manufacturer of memory. So what are the additional conclusions that they came to? Well, first of all, the uncorrectable average was 1.3% across their fleet per year. So now there's kind of always a question as to how big is the Google fleet of servers. So let's just say there's 100,000 machines in their fleet. Okay, so that's 1,300 failures a year, uncorrectable failures. So if we divide that by 365, we had 3.5 failures every single day in their fleet of servers. Okay, 3.5 failures. Now if they've got 1 million servers, that's 35 failures a day. Okay, and you can see some of the platforms experienced twice that failure rate. Okay, so if it's 100,000 servers, we've got 7 failures a day. That means we've got to bring that server down. What their methodology is, they swap out the memory. They've got to bring it back online. That's significant. That is a significant number. So reliability is a big deal nowadays. And that's where I got very interested in this because my customers were seeing the same type of thing. And so we decided to design some equipment to help them. The other interesting conclusions was that temperature had a very small effect on their error rate. They also said that newer generation DIMMs did not show a worse error rate as they commonly had feared. So they had 3 different types of technology. They had fully buffered DIMM, DDR1, DDR2, and they didn't find a conclusion, a big difference between the different technologies. So that meant, like I think somebody had asked the question, do you see more failures as we went faster with the memory? Well, they did not experience that. So what we're offering up is a kind of a paradigm shift for memory compliance testing. This study was done in 2009, so they didn't have the advantage of the newer tools that we have today that can automate protocol compliance testing, as we say, in the wild, okay, which means in the setting that the machine was designed to be used for, running the customer application. A lot of this test equipment you see has to be used in more of a laboratory environment. Okay, so what we've come up with is a piece of test equipment that can be used in the wild. So their conclusions could not find a source of this unexpectedly high error rate. So there's the challenge. There's a challenge for us in the industry. Why are these types of errors occurring? So improvement in the error rates is critical, obviously, to our industry that we're all a part of, if we're going to rely upon these large fleets of servers. So first of all, let's take a look at what is protocol compliance. What am I talking about when I use the phrase protocol compliance? Well, it's the correct timing between events on the memory bus. Now, from my perspective, that means events that occur on clock tick boundaries. So we didn't take a look at, let's say, setup or hold times, okay, which would be, the data valid prior to the clock edge or after the clock edge. That was a little bit more of an SI type of issue. So we look at timing between events. For example, read operation followed to closely by a precharge. Okay? A write command followed too quickly by a read command. That might be some bus contention issues. And also average refresh rate, a big issue for servers. So those are the types of things when we talk about protocol compliance that I'm referring to. So a little bit about our study. So we used commercially available motherboards, right out of the Best Buy, or in some cases customers would send us their newer motherboards, CRB platforms that they would want us to take a look at. We used our DDR3 detective, and in this case we use a DIMM. So you can see there, maybe I can get this pointer to work here. Down here is our interposer. Now Jenny talked a little bit about these interposers. So the connection here we have is just the address command control to the DDR3 detective. So we don't connect to the data in this case. So you might say, well, why don't you need to connect to the data? Well, in order to understand the protocol, you really only need the address command and control. Right? You know where the data is going to be on the bus. If you understand the latency, if you understand what type of command you're executing, you then know where in time that data is going to be on the bus. But when you're running a customer application, you don't know what the value of the data is. And really, you don't care. Okay? You just want to be able to take a look at the timing of the events on clock tick boundaries and understand, do we have things that are too far apart or too close together? Because if those types of events occur, that could be a problem. So we are commercially available motherboards. What did we see? Well, here's an example. We saw these types of violations. For example, violation 4, a read too close to a precharge in the same bank. What we can do here is look at every single clock tick. So with an onboard FPGA, which of course has been a great enabling technology, what we can do is we take a small bit of current off the bus, we put that into our FPGA, and we are able to, on every single clock tick, look at every rank, look at every bank, and look for all of these conditions simultaneously. So if anything occurs, we're going to see it. So if it's an infrequent event, we're going to see it. And these are the types of violations that we saw really on commercially available motherboards. You can come out and see some of the stuff we have out in the demonstration booth. So let's take a look at some specifics. Okay, so here's something that we found. A read followed by a precharge, rank 0, bank 5, separation fails by 1 clock tick. Okay, so what we did was we can take the trace here, we can filter out the deselects just to make it easier for you to read, then we can trigger exactly on the violation. And we can show you all the traffic that's going around in between. So you might say, well, what are the problems? Why is this a problem? So what? It's a read too close to a precharge. Well, how critical is this? Well, a precharge closes a bank. Read latencies dictate when the data is to be returned. So a command telling the bank to close could be coincident with the data being returned from that bank. Okay, so maybe this occurs 100 times a minute, thousands of times an hour, okay, millions of times over the course of a week. Could these types of protocol violations occurring so frequently over time statistically end up with corrupting the read data coming back? Okay, so that is the hypothesis. That is what we are starting to find out in the industry. We're now at a point, we've had this tool out for 18 months, we're able to see now all of these violations simultaneously. In the past, what engineers used to do was they used to hook up a logic analyzer and they used to look for one violation at a time. Okay, and that was obviously extremely laborious. Okay, every bank, every rank, every violation, how long would you let it run? Would you be running, what type of software? Would you be voltage margining? Would you be in a temperature chamber? Obviously, this type of situation allows for us to take this type of analysis one step further and give quick insight into what's going on. So let's take a look at another violation that we saw. So a write followed too quickly by a read to the same rank. Okay, so you can see the violation there. In this case, we left the deselects in. I guess my pointer doesn't work so good anymore. We left the deselects in the trace so you can, oh wait, wrong pointer. Here we go. We left the deselects in the trace so you can see those, but you can take the deselects out of the trace. You can make a little bit better use of the onboard memory. So why is this critical? Well, the parameters for the separation of the reads and writes are based on the latencies. The data bus is shared, and overlapping of the events can lead to data corruption. Now, we don't know when we're running in the wild, okay, when we're running in the customer site, exactly what the data pattern should be, okay? But we do know when we see a system crash, okay? And like Jenny showed in hers, we can work from the crash, we can work backwards. Now we can actually see if any of these violations ever occurred, okay? And actually, we were at a customer site. Actually, it was in Shenzhen last spring, where we had a customer that had some test software. It was very rigorous test software. And it was exercising the system, and it crashed. We did this exact analysis. We worked backwards, and it was a read too close to an activate. Okay, so these types of things now would not occur in this particular system unless there was a lot of traffic going on, a lot of events. So all of these events combined created the statistical probability that the read was too close to the activate. So again, when we're looking for data corruption, we don't know what the value of the data is when we're in the wild, okay? But if we did know what the value of the data was, we can hook up our logic analyzer and we can look at the actual data values. The other thing, we can continuously trigger a scope. So if this is something that's happening quite a bit, you can continually trigger a scope, and our delay through our box is a constant 60 clock ticks. So you can put your scope probe on various signals on the bus, and you could see whether you had some, charge left or any type of bad signal integrity on your bus under these circumstances. So you could actually isolate it a little bit further. Okay, so another violation, going through some of the violations that we've seen, a write command followed too closely by a precharge to the same bank. Okay, should be 26 clock ticks. I think we failed that by 2 clock ticks. And again, you might say, oh, what's 2 clock ticks amongst friends, And again, this may not cause a problem today, may not cause a problem tomorrow, but what happens when that occurs millions of times in a week? What type of effect does this have? And now you have 100,000 servers and maybe 1 million servers. Could this possibly be the source of some of these uncorrectable failures? So how critical is this? Well, a precharge closes the bank. So the DRAM is not expecting that precharge command and may depend on that time to complete the write. So thousands of times per minute over months and years of operation could lead to data corruption. So another usefulness of this tool that we found is memory vendors who get parts sent back to them. Okay? And they say, hey, they're always pointing the finger at us, the DRAM vendor. So they like to use this tool to show, hey, it was the memory controller. If you're not obeying the protocol, if you're not treating us correctly, we could have a failure. Okay, so it is kind of the judge when it comes to the finger pointing between the memory controller and the DRAM vendor. So here's another example, an activate command too soon after a calibrate command. Okay, this situation, we were 68 clock ticks and we should be 75. So again, most of these violations were events occurring too close together. So calibration commands, well, the purpose of the calibration command is to account for the voltage and the temperature variations. So right from the spec, we can see no other activities should be performed on the DRAM channel by the controller for the duration of that time limit. The quiet time on the DRAM channel allows accurate calibration of the output driver and the on-die termination. So if the DRAM does not expect that activate command, it might be missed and the row not opened. So the last example I have here is a study of refresh. Okay, so refresh, if you don't refresh enough, that's a problem. You're going to lose state. If you refresh too much, you're wasting performance. So the purpose is to maintain the integrity of the stored data. That's why you want to refresh just right. If you refresh too much, you're going to waste power and bandwidth. You're going to leave a lot of extra performance on the table. I visited a customer site who was using this tool, and he said, listen, Barbara, if you can save me 1 clock tick out of 100, meaning you're showing me where I need to tune my system a little bit better. 1 clock tick out of 100, that's a 1% performance improvement. That's a big deal for us in the server business. Okay? So now that we have the ability to count these things real time, very, very quickly, we can give a lot better insight to our industry, and we can take our industry one step further. So performance metrics. The other thing we see now, okay, so we have violations. How much violations do we have? Do they really play a role in failures? How about performance? How about power management? Well, this tool has a lot of counters in them. Some of the customers came to us and said, gee, let's use those counters for a couple other things. Let's take a look at power management. How often are we going into power management? What are our data bus utilization? And we want this in real time, continuous. We never want you to miss a beat. We want to be able to run this software. We want to be able to look at these counters, tell us what's going on. So we also built that into the system. And again, this has been able to give a lot of insight quickly to the customers to take our industry to the next level. So to just summarize, real-time protocol compliance analysis of this time is now possible. And as Jenny reviewed, the difference between this tool and maybe some of the other tools that you see is a lot of the tools will grab a large amount of trace memory and they'll sift through it and they'll look for violations. Okay? Well, we liken that to emptying San Francisco Bay with a bucket. Okay? Not the right tool for the job. Okay? You're going to be there for a long time with that bucket emptying San Francisco Bay. Okay? The real-time tools with real-time counters look at every single clock tick. Nothing is missed. So you're going to get to the source of your problem a lot faster. The designers can now make systems more reliable, and you can gain a better understanding of compliance and performance metrics. So like in the past, we've never really been able to, look at refresh rates so quickly and so easily. So now we can do all sorts of things with these onboard counters. So as memory technology becomes more critical, obviously in our society it's becoming huge, this insight will help us make better specifications and provide better products. So that's all I have for my talk. You can come out and take a look at our demonstration and take a look at our website for more information.
All right. Well, let's thank her for a terrific presentation.
Thanks, guys.
So